measured the watts going into the soldering iron under normal conditions, and then we stuck the soldering iron in a cup of ice, and the amount of watts going into it didn't change, so we concluded that there was no temperature control system in the soldering iron. This is the results or a temperature profile, and as you can see, the farther out you go from the base, the lower temperature. And these lines are different power settings that the soldering iron was on, and it ranges from 25% power to 100% power. And as the power increases, the difference between the base and is more dramatic. This is the results of the heat convection coming off of the rod, as well as the calculated Qmax. And this top green line right here is the power supplied, and the power supplied to the iron did not increase as the knob was turned. So if we turn it up maybe halfway, the power supply wouldn't be half of its max. And as you can see, that the more power was applied to it, the lower, or the bigger difference between the Q convection and Q max. So that resulted in a decrease in fin effectiveness and fin efficiency as the power was increased. And you can see they pretty much follow each other. In conclusion, as we already said, power supply was not linear, and the rod had no temperature control. And we saw the greater the temperature difference between the base and the tip, the increase in power led to a greater temperature difference between the base and the tip, and a greater loss in efficiency and effectiveness. These are my sources for the fin theory. Any questions?
Dr. Henry asked me last week to do a presentation on my country, and since he didn't specify what I should present on, I decided to present on the two major power resources in Iceland. So I'll talk a little bit about the country, its development, and